Anyways.
Enough horror stories.
So as far as demo goes, could you guys just explain what your goal was and what you did and then show it off?
Yeah.
We have a slideshow.
Wow.
So,
Really?
yes, we love a good PowerPoint. Okay, so hello. You know all of us. And our overall project was to be graphing LSystems specifically on the FPGA. This is our team. Special shout out to Beep Boop, our FPGA. He really came through. And yeah, we'll just go a little bit over what an LSystem is first, and then our general workflow. So first, an LSystem is generally a self-repeating pattern that's composed from a series of strings. Each character in the string will describe a action in the state of graphing. So like, should it be going forward? Should it turn left 90 degrees? Should it turn right 60 degrees? It really depends on the LSystem, but basically each character will represent something. There are also characters that will create more rules, and then the string itself will exponentially increase, so then the design can grow increasingly more complex. So first you start with an axiom. This is a smaller string, maybe only a couple characters, and this will serve as the basis, kind of like the root string out of all of the LSystems. So this is like the simplest pattern in the entire repeating pattern. Then in order to modify the string, you have rules. Each rule will take a single input character and then replace it with a certain number of characters. So like, for example, you have X, it might replace it with like a series of like X's plus minus like forwards. So then at every replacement of the character, the string will grow larger and larger. And then iterations. So this makes the system recursive because once you process an entire string, right, you apply a rule to every single character, there's kind of nowhere to go from there. But an LSystem would be relatively boring if you only pass through the string once. So by increasing the number of iterations, you then start with the string from the previous iteration, the previous recursion, and then you can grow the string from there, and then again, make a more complex thing to graph, and then the pattern will grow across the string. But with that is the caveat that like the string grows larger. It takes a lot more time to process and to graph, but overall it'll give you like a more interesting pattern.
Next, for our workflow. So overall, our goal was really, like what Caitlin said, to be able to graph these recursive LSystems in like with timing that rivals the baseline Python. So yeah, so our baseline was like a Python coding set, and then we translated that over to C just so we could get a better idea of what each module actually did and what modules we wanted to include in our Verilog implementation. So we had multiple versions of our Verilog implementation. So the first one was not recursive, it didn't have M10Ks, and it was like based on registers. And this was able to do one iteration and allowed us to optimize the translation abilities. So like the actual application of the rules, as well as being able to optimize how we're passing characters from module to module. We'll explain like our top level and our like sub modules in a bit. But we were able to optimize all of those before we implemented like recursion. Then we were able to implement M10K blocks. So those are going to hold the values or the those growing strings that are recursively generated at each iteration. And then finally, we were able to, within like graphing, implement more complicated LSystems with different graphing rules. So some of which are like based on 90 degrees, some of which are based on 60 degrees. I think we have one that's 120 degrees. And we also have like through the serial input, the user can interact and like decide like which LSystem, what the axiom should be, and some other criteria as well.
So at the lowest level, we have our rules module, which takes a individual character and the type of L system, and then will apply the corresponding rule to the character. So the character is a singular byte, but our output of the rules module is 10 bytes. So this allows us to apply larger rules up to 10 characters to for a variety of different L systems. So currently we have a Dragon Curve, a Koch Snowflake, a Koch Curve, a Sierpinski Arrowhead, and oh god, there are two others.
A cross and then a tessellated triangle.
Although those don't work as well currently. So we instantiate this rules module within our create system module, which is a 14-state FSM. The create system will receive an initial axiom from the top level, and then proceed to perform a certain number of iterations on that axiom. The axiom is fed and then shifted character by character into the rules module, and the result is written to a initial M10K block. For subsequent iterations of the L system, we fluctuate between two different sets of M10K blocks. So after the first iteration, we read from A and write to B, and then we read from B and write to A. Each M10K block is each dual port RAM module consists of a multitude of M10K blocks containing 2 to the 12th bytes for 2 to the 12th characters. Yeah.
So then for the top level, so this is where we hold our graphing functionality and we have our instantiation of the create system module. So we have a 10-state modular FSM for graphing. And when we say modular, we mean that the FSM will go to different states based on which graphing functionality is needed. And we're only plotting the last iteration's result instead of plotting the intermediate iterations. And that's for many reasons, partially because we don't want to have to clear the screen every time because we'd have to switch control, the VGA screen control from the HPS to the FPGA and back again. As well as like dealing with clearing the memory. We don't want to have to be doing that in between, like, or while it's still running. So yeah, as we mentioned, we can graph at 90 or 60-degree increments, or 120 technically for one of the cases. And we communicate with create system via val-ready interface so it is waiting for the pixel to be, not the pixel, the specific character to be translated through the whole, through like the whole pipeline pretty much. And it also has the PIO ports that communicate with the C, which we'll talk about on the next slide. In addition to like the graphing, like physical graphing, like we also allow for calculations past the screen edges. So we have a bound that stops like graphing from happening when we're past like the 640, 480, but we allow calculations to continue so that if the, I guess the shape continues around and like returns back to the graphing region, it's able to still be plotted accurately.
And then just to like go back to rules.v, the signed molt block that we have that does 11.21 fixed point, that's specifically only used for the graphing at 60 degrees, just to make sure that we have like a good slope. but nothing else in terms of our like addressing to pixels on the VGA is done in 1121 fixed point. We just use it for creating a nice line.
Yeah, so it's defined within rules.v, but we only ever use it in the top level.
Yeah. So then going on to the C code. So as Priya mentioned, this is like our interface with the FPGA. So we have some output PIO ports from the HPS side where you can choose one of the 6 LSystems. It then prints out like what the recommended axiom is and like the characters that will draw, meaning which ones will like draw a line moving forward and which ones will generate rules. So if you really wanted to create your own axiom, you could. Then you can input the axiom, the number of iterations, the line length, which based on the type of L system, so whether it's drawing in 90-degree or 60-degree increments, there are certain bounds on the length, just because we noticed that like for drawing in a straight line, you only really need like 3 pixels for it to look like a line, whereas for drawing a diagonal line, you need like around 7. Then line color, just for fun, that gives it a 1 byte hex code value, and then the starting coordinates within the bounds of the screen. And then outputs from the FPGA, also from a PIO port, is just the timing in terms of clock cycles. So that's something that's incremented throughout the Verilog code. And then on the C side is translated to seconds. And then we have additional functions. So once the L system is initially plotted, then we allow for zooming in and out, as well as panning around the screen, just so you can see more of the L system in various parts of the screen. And then in terms of limitations, so the first is the block size. So as we mentioned before, our dual port RAM is around 8,000 bytes. But when it comes to the L system, because it grows exponentially, there is going to be a point where the string itself is more than 8,000 characters. So when that happens, it'll actually graph as much of the string as it can, but it won't end the system. And that's just because it's waiting to get to a block in the M10K that hasn't been written to yet, that has a value of 0. But because we've already overflowed the memory that we've allocated, it'll just like keep wrapping around. And then the diagonal lines, like as we mentioned before, like they're being graphed like kind of pixel by pixel. We could have done like an actual line drawing algorithm, but in terms of time, we decided that that was not really worth it. So instead we kind of toggle between drawing in the X direction and the Y direction. So then because of that, there's a certain level of resolution that you need to have in order for the line to look relatively diagonal.
So then for 32-bit addressing, so 32-bit, so that's like what the VGA, the drawing command needs to plot the XY coordinates. And that's like far more than enough to plot on the screen. Only 10 bits are needed for the 480, 640 screen. But since we're doing the calculations outside of the screen also, we're going past just the 10 bits and the 30-bit can easily be like 32 bits can easily be hit like at very high iteration counts if we're going like way past the screen and also depending on how long the lengths of the line are. As for negative coordinates, so when we first set up like the X, Y, and all the graphing variables, we made them unsigned since we were just thinking about being able to graph on the screen. But since we then decided to be able to do the calculations outside of the screen, that becomes a problem when some of them are negative. It causes overflow, which, there's like overflow where like it thinks it's like a bigger number, so then it draws like a line down the screen. So that's something that like in the future we'd like to implement. We would want to like refactor the variables and make them signed so that we'd still be able to continue doing the calculations outside of the screen while maintaining the like values.
So I guess it's time to demo. For this, we'll be showing.
If you guys have any questions before we move on.
Oh.
Yeah.
Not at the moment. No,
not at the moment.
Looking forward to seeing the demo.
Okay. So for this, we'll be comparing our FPGA setup against a Python script, which was our baseline. So as Caitlin previously mentioned, when you start up the code, you'll be presented with a variety of LSystems to choose from. In this case, we'll be choosing the Dragon Curve to start off with. And then we provide some information about the LSystem you've chosen, including the default axiom, characters which are affected by the system, what characters are available to you, as well as what characters will actually cause something to be drawn. So then from there, you can input your desired axiom, the number of iterations, as well as your line length and color and starting position. And then after inputting a character, we'll present the time to visualize, as well as the ability to zoom in, zoom out, and pan to a different set of coordinates. So if we zoom in, this is a 11 iteration dragon curve, and we'll be shifting it slightly to the left. And then we can zoom back out.
Basically, what happens is when we're zooming in or zooming out, we're adjusting the length on the C end. So if we're zooming in, we're multiplying the length by 2. And then if we're zooming out, we're dividing the length by 2, but also keeping in mind the bounds of the length, as we previously mentioned, just to make sure that like drawing a straight line looks like a straight line, or drawing a diagonal line looks like a diagonal line.
When you zoom and pan, is the whole curve recalculated?
Yeah.
Okay.
Yeah. So yeah, that's something important to note. The actual length of the lines don't seem to drastically affect the computation time on the FPGA. So like when we zoomed in, or the original time was about 3.6 milliseconds. But when you zoom in, the line length is much larger, and yet it is still around 3.6 milliseconds. And then if you were to compare that to the Python code trying to generate 11 iterations, a step size for Python of 10 would take 62 milliseconds to complete 11 iterations, but a step size of 4 would take 48 milliseconds. And an 11 iteration dragon curve has 8,190 characters in it, which is just about the maximum size that we can hold in our M10K blocks.
We're looking at something like a factor of 16 or 20 faster, something like that.
Mm-hmm.
Yeah.
Yeah, so we can go through the other LSystems too. We found basically the maximum number of iterations that each of them can handle, because some grow way faster than others. And then we as Michael mentioned, we compared it against the Python code, which is obviously a little bit more able to count the number of characters that it's generating, just so we can see okay, it's reaching the capacity of our M10K block. So that's why we can't do any more iterations.
It's gorgeous. That dragon curve looks gorgeous.
It does. It's really nice.
Yeah.
Okay. So we can do a Sierpinski arrowhead.
Right. And then
have you played, I see that axiom is a user input. Have you played with just random axioms and seeing what gets drawn?
No.
We played around with different axioms mostly when we were doing our before recursion implementation, because that allowed us to see if they were being translated properly. But since we've had recursion, we haven't really been playing around with that.
Gotcha.
Nice.
Yeah. And it'll accept a bunch of different characters, and then in the Verilog side, it'll only apply the translation based on a new rule, or the graphing actions on specific characters. So you could theoretically put in random characters and it just would ignore them.
Okay.
And so yeah, the Sierpinski arrowhead at around 6 iterations takes about 800 microseconds. On on the Python code, it takes about 16 milliseconds. So again, about that factor of 16 faster, 16 to 20.
I guess just as a brief aside, the place that the Python actually beats the FPGA is in terms of the length of the string. So as we mentioned, the R code is limited by the size of the M10Ks, but the Python is able to do much more. There was one, I don't remember which curve it was, but when we were trying to find out the length, how many characters it was, we pasted it into Word and it was 12 pages.
Yeah.
So
I think it was the Sierpinski Triangle where after 6 iterations, it gets 6 iterations, I think is around 4,000 characters.
It's 2,186.
Okay. And then 7 iterations, it grows to 16,000, which is crazy. But yeah. Oh, okay. So here, this is kind of showing the issue that Priya was mentioning before about the negative value. So you can see a graph because basically the top level is receiving the characters from rules.v, so the create system module that Michael talked about. It's receiving it byte by byte. So as it's receiving a character, it's drawing, although it's really fast, so you obviously can't see it drawing the actual line. But in this top right corner, the snowflake is kind of growing up. But because it's above the top of the screen, it's reaching negative number territory. So even though it looks like it graphed really nicely, because now it's in a negative number, it then becomes a super increasingly large 32-bit number. So technically what's happening right now is it's trying to calculate and graph stuff all the way very much below the bottom of the screen. So it's still doing stuff. It just takes a lot longer because the numbers are so huge. And then sometimes in the cases where it does reach back to the X and Y values of the VGA screen, it'll draw a straight line, just because it wasn't expecting that number to be as large as it is. And so it'll just try to draw across the entirety of the screen. Yeah, so as you can, the straight line that I mentioned happened. But yeah, and then I can show the 2 other LSystems that don't look as great. Mm-hmm. And it's basically, I think, due to our graphing limitations. So the first one is the cross, which is basically just a dragon system with more blocks, I think, completed. So the cross itself actually grows really quickly, which is why the number of iterations you can have is 4. But what it looks like in the Python is a little bit more filled in, but yeah, it just basically creates a bunch of scripts.
Interesting.
Yeah, so it's supposed to be more of a filled in blob.
The left half of it should have more squares in it.
Yeah.
We're honestly not really sure why it doesn't work.
Yeah. And then, but we do know that the next one I can show you is the triangle, the tessellated triangle. It doesn't work for us because we do limit the length of the sides. And even on the Python at a small length, it looks really gross. I think it's just based on, the actual L system itself. It has to be a line length of around 50 for it to look anything other than just a group of triangles.
Okay.
Yeah, so even on the Python, it kind of looks like this, unless you make the side length 50, like I just said. But we're limited by the, our side length at least is limited by the size of the PIO port. So theoretically, that's something that we could go back and change, but this is what it is now.
Yeah.
So that's a lot more from the last time we met in lab, which was not that long ago. You guys have implemented a lot of these L systems in a short amount of time.
Yesterday, wasn't it?
Yeah, it was we finally figured out, I think what happened in the past couple of days was we finally figured out the M10Ks and we like had that hammered down. And then what we were trying to make sure happened was creating the computations like outside of the widths of the screen, which was really weird to think about. But then I think once we thought about like bound checks, it made it a lot simpler. And then the way that we made our code was really nice in that, like, since we have a separate module for the rules and then like a separate module for the actual like applying of the rules, all we had to do was just create a new state in the rules module and just say like, oh, if you see an F, you should do this, this, this. And then we just had to put a couple if statements here and there to just say like, oh, if this LSystem number is like that of a dragon curve, it should draw straight lines rather than like 60-degree lines. So like, I think the way that we made our code was relatively modular. So then once we got like the baseline, it was really easy for us to add just like a bunch of LSystems.
Well, it looks really good. That dragon curve in particular is really gorgeous.
Very nice.
Should we quickly compare it to the Python, at least for Dragon?
Sure.
Sure.
So our Python code is actually really similar to the way we implement the code in Verilog. So I'm just gonna, what should I make the step size, Michael?
11. Step size, either 10 or 4.
We can do 10.
What's the, this is running on a laptop?
Yeah.
So,
yeah, this is just on Caitlin's computer.
Yeah. So this is printing out the length of the output string. So here you can see it's 8,190. So it's like just missing the size of our M10Ks. And then, as Michael said, it's like 61-ish milliseconds. Yeah.
And the graphing.
so
and you can see the picture from it.
True.
Yeah.
Ooh. So it looks the same.
Looks the same.
looks the same, which is so the clock rate of your laptop is probably between 2 and 3 gigahertz, and the clock rate of the FPGA is 50 megahertz. So it's impressive that you're a factor of 20 faster. Now, it's hard to compare those because Python's an interpreter and who knows what it's doing.
Right.
Still, in terms of, say, total energy used, the FPGA is a clear winner because it's probably running at maybe 500 milliwatts, and your laptop is probably running at 20 watts. That's a really pretty curve. It's really, it came out nicely.
Thank you.
So, if you chose 8 M10K blocks instead of say 16 because?
Oh, we actually do have a reason for that. So in order to, so you might have noticed like when we were doing the serial input, we were able to like directly go into like the next LSystem. So that's because we're clearing the M10Ks at the beginning of the rules.bfsm or create system FSM. And the bigger the M10K or the dual RAM ports are, the longer that takes. Like it, yeah, it just takes a longer and longer time since they're just so much bigger.
But still, it's only milliseconds, right?
Yeah. It seemed to take a lot longer when we were having the issue of graphing off the side of the screen. But yeah, I think for us, like in addition to the fact that we're clearing the M10Ks every time, there's going to be a point where like the string is too long to graph on the bounds of the existing screen. And since we do have that like negative quadrant issue, it wouldn't really scope out well, if that makes sense.
So every factor of 2 in number of M10K blocks buys you like 1 iteration.
Yeah.
So to get to 20 iterations, you would have used up all the M10K blocks by far.
Yeah, no, it's kind of crazy. When I pasted the number of characters and saw that it was like 12 pages at one time, we were all very shocked because we didn't expect the string to grow nearly that fast, but especially in the like the Koch curve and the Sierpinski arrowhead, because the rule generating functions are on one character, and like, for example, one F will create a string with 4 Fs. Like it really blows up very quickly.
Very cool.
Looks awesome. Yeah.
Yeah,
really
very
good
nice.
job.
Cool. Nice.